Welcome to The Explainer. Today, we're tracing the story of large language models. We're going to follow the single architecture that completely took over an industry, from its roots in academia all the way to the huge multimodal models we see today. And we'll do it by going straight to the source, the original research papers that marked every single turning point. Let's get into it.
At the heart of this whole story are two really big questions. First, how did one single architecture, the transformer, become the foundation for pretty much the entire AI industry? And second, what does its crazy fast evolution tell us about where we're all headed next? This is the core mystery we're going to unpack.
All right, so here's our game plan, broken down into 6 parts. We'll kick things off with the early foundations, and of course, the arrival of the transformer. Then, we'll get into the scaling revolution it kicked off, and the absolutely critical step of making these things actually usable. From there, we'll look at the engineering that made them practical, explore today's multimodal frontier, and then finally, we'll look over the horizon at what might be coming next.
Okay, let's dive into part 1, the foundations. Before we had these giant models that could write code and poetry, researchers had to solve a much more basic problem. How do you get a computer to understand what a word means? This is where our journey really begins.
You can really see how we got here step by step. Back around 2013, you had models like Word2Vec, which let us turn words into mathematical vectors. All of a sudden, you could do arithmetic with concepts like king minus man plus woman equals queen. It was a huge deal. A year later, sequence-to-sequence models came along, which let us work with inputs and outputs of different lengths, a total game changer for things like machine translation. But, and this is a big but, both of these had to process things sequentially, one word at a time. That created a major bottleneck and set the stage for the massive breakthrough in 2017.
And here is the core idea that changed everything. On the left, you have recurrence. Think of it like reading a sentence one word at a time. It's slow, and it has a really hard time connecting a word at the end of a long paragraph to one at the beginning. But on the right, you have self-attention. It looks at all the words in the input at the exact same time, in parallel. It can figure out how every single word relates to every other word all at once. This wasn't just a small improvement, it was a fundamental shift. It blew up the sequential bottleneck and replaced it with something that could run incredibly fast on modern hardware like GPUs. And that, right there, changed everything.
The title of the paper that introduced the transformer really said it all. Attention is all you need. This wasn't just some catchy phrase. It was a bold declaration that the entire field could finally move on from that slow, one-word-at-a-time processing and start building on a whole new foundation. A single idea that truly changed the world. So with that architectural bottleneck totally shattered, the race was on. The next era wasn't about inventing a brand new architecture. Instead, it was all about one question. Just how big can we make this thing, and what happens when we do? Welcome to the scaling revolution. In this new era, 2 main playbooks emerged for pre-training these models. On one side, you had models like BERT. They use a technique called masked language modeling, where they look at text in both directions to fill in missing words. This makes them amazing at understanding context for analysis tasks. On the other side, you had the GPT family, which is autoregressive. It only looks backward to predict the very next word, which, as you can imagine, makes it perfect for generating text and learning new things from just a few examples. These 2 approaches really set the stage for the kinds of models we have today.
For a while, the mantra was just bigger is better, just keep adding more parameters. But then this hugely important paper from DeepMind in 2022 called Chinchilla came along with a critical insight. It turned out that for a given amount of computing power, everyone was building models that were way too big for the amount of data they were trained on. The sweet spot was actually to scale the model size and the training data together in a lockstep. What that really meant was that many of the biggest models out there were actually undertrained. And that discovery completely changed how the entire industry thought about building LLMs.
So it's one thing to have a powerful, scaled-up model, but it's a completely different challenge to turn it into a useful, safe product that people can actually use. And that brings us to our third section, the crucial process of aligning these raw prediction engines with human intentions.
The alignment process itself has evolved incredibly quickly. The first big technique was reinforcement learning from human feedback, or RLHF. This is where you have actual humans rank different model outputs, which then trains a little reward model that you use to fine-tune the main LLM. But as you can imagine, that's slow and really expensive. So the next step was RLAIF, where you use another AI, guided by a constitution or set of rules, to provide the feedback instead. It's way more scalable. And even more recently, we've seen simpler methods like direct preference optimization, or DPO, pop up, which can get you similar results without all the complexity.
So what's the goal of all this work? Well, it usually comes down to these principles. You want the model to be helpful, to actually do what you ask. You want it to be harmless, so it avoids generating dangerous stuff. And you want it to be honest, which means not just making things up. But this is a really tough balancing act. There's this constant trade-off. If you make the alignment too strict, the model can start refusing to answer perfectly normal questions, or it can just lose its creative abilities. This is still one of the biggest challenges in the field today.
Okay, so we have a scaled, aligned model. But these things are absolute monsters to run, computationally speaking. I mean, they're huge. So how do you actually operate them in the real world without it costing a fortune? This is what our fourth section is all about, the efficiency imperative and the system-level tricks that made LLMs practical.
This brings us to the unsung heroes of this whole revolution. These aren't new model architectures, they're really deep, clever software optimizations. Flash attention, for example, redesigned the core math of self-attention to be way faster by being smarter about how it moves data around on the GPU. Page detention, which you see in systems like VLLM, solves a huge memory problem called the KV cache. Then you have speculative decoding, which uses a smaller, faster model to draft text that the bigger model just verifies. And finally, quantization techniques like QLoRa let these models run with way less memory by using lower precision numbers.
And the impact of these optimizations is just massive. We're not talking about small percentages here. We're talking about a 2 to 4 times improvement in throughput, basically how many people you can serve with the same amount of hardware. This is the stuff that turns a multi-million-dollar research project into a viable product that can be deployed at scale. It's the engineering foundation that today's AI products are literally built on.
This brings us right up to the cutting edge, where we are today. All those efficiency gains we just talked about were the key that unlocked this next leap. By making these models cheaper and faster to run, it suddenly became possible to expand what they could do, breaking them out of the text-only world and massively increasing how much information they can handle at once. This is the multimodal frontier.
The scale of progress here is just staggering. I mean, just a few years ago, a context window of 2,000 tokens was considered normal. Today, we've got models like Llama 3.1 handling 128,000 and Gemini 1.5 Pro pushing 1 to 2 million tokens. That's like feeding it an entire book series or hours of audio in one go. And look at the modality column. We've gone from just text to fully multimodal systems like GPT-4o that can handle text, images, and even real-time audio, all at the same time.
So why does all this matter? What does it actually let us do? Well, it means a model can analyze an entire hour-long video or a massive software code base all at once. It makes real-time, low-latency spoken conversations actually feel natural. You can ask it to perform really complex reasoning that requires it to pull information from hundreds of pages of documents. And maybe most importantly, this is the foundation for creating more agentic systems, models that can use tools and APIs to get things done in the real world.
So we've seen where these models came from and where they are right now. For our last section, let's look to the future. What are the big problems and research bets that are going to define the next wave of progress? What's coming up next on the research horizon?
So this is where the smart money is going. There's a huge focus on something called test time compute, basically making models think harder when you ask them a question, instead of trying to cram all knowledge into them during training. Second, since we're kind of running out of high-quality data on the internet, data curation and creating high-quality synthetic data is becoming the new bottleneck. We're also seeing a massive push for powerful on-device models that can run offline, right on your phone, for privacy and speed. And finally, the community is trying to move toward live benchmarks that are always being updated to fight against models just memorizing the test.
And that brings us to our final question. We've seen progress come from all three of these areas. The transformer was a new algorithm. Chinchilla showed us the power of more and better data. And of course, GPUs made this whole scaling revolution possible. So where is the next massive leap going to come from? Is it going to be a totally new architecture, a breakthrough in data synthesis, or maybe a brand new kind of computer chip designed just for AI? That is the multi-trillion-dollar question.
Everything we've covered today is built on decades of incredible research. If you want to go deeper and read the original papers that sparked each of these breakthroughs, we've put a full list of references for you in the description. Thanks so much for joining us.